Okay, so back to business. Molecules can be elements, they can be compounds, but regardless of whether they are elements or compounds, Kai and Jack, can you guys pay attention, please? Regardless of whether they are elements or compounds, they are always made of two or more atoms. Yes? Two or more atoms. The atoms within that molecule are bonded covalently. What is happening with the electrons if they are bonded covalently? Yeah, the electrons are shared. Point number 6 is an enriched point. You don't really need to, explain this if you're not doing the enriched portion, because the word definite composition sometimes sounds a little funny to people and it confuses them, but all it means is that water is always 2 H's and 1 O, exactly. It's never going to be 4 H's and 2 O's, right? It always has an exact makeup, yes? Whereas if we have sodium chloride, remember if we have a small crystal, we might have Na100, Cl100. But if we have a bigger crystal, we might have Na a billion, Cl a billion. So that is not a definite composition because it could be bigger or it could be smaller. Water can't get bigger, water can't get smaller. It's always just 2 hydrogens and 1 oxygen. Ionic compounds do not form molecules. Why not? What do ionic compounds contain? They contain metals. What do the ionic compounds do with their electrons? Do they share their electrons or do they transfer them? They transfer the electrons. So they're not molecules. Some other enriched points, but I'm going to bring them to your attention because you will hear these words come up again. All right, in liquids and solids, you know how the molecules are closely packed together? They're really tight right next to each other. In between the molecules, do you remember what inter means? Inter means between. And obviously molecular means molecules. Yes, of course. So if there are forces in between molecules, we call those intermolecular forces. So if I had a water molecule here, and I had another water molecule right beside it, the force between the molecules are called intermolecular forces. And remember, the abbreviation that I use for molecule is MC. What does IMF stand for? Intermolecular forces. Okay? And those are very weak. Okay? So when a molecular solid melts, like let's say we had our two water molecules there and they were together as a solid, within the molecule we would have covalent bonds, right? You would have a covalent bond and a covalent bond, a covalent bond and a covalent bond. If this was to then melt, whoops, not melt. If that was to melt, the forces between the molecules would break. So they would separate from one another a little bit. Yes? So they're more separate. But the molecules, the water molecules, don't fall apart into oxygen and hydrogen. You don't end up with like individual atoms. Does that make some kind of sense? The covalent bonds are really strong. So if I'm a water molecule and this is, oh look, I got leftover containers from lunch that never made it back into the lunch kit, so they should today. If this is a hydrogen and this is a hydrogen and I'm an oxygen, and I am bonded to another water molecule over here by intermolecular forces, if it starts to heat up and I turn into a gas, woo, I go flying off, but these stay attached because these bonds are really strong. Covalent bonds are really, really strong. Is good? Or is confusing? Is good? Okay. And if it's confusing, guess what? It's a black diamond, so you don't have to worry about it, okay? When molecular solids melt, it is intermolecular forces that break, not the covalent bonds. When molecular liquids boil, it is those intermolecular forces that break, not the covalent bonds. So the molecules stay intact, they don't break apart. So there's 9 points. Now we're going to go into each of those 9 points in a little more detail. Here's just a ton of molecules, so you can see the huge variety that they come in. But what you'll notice about every single one of these is that they're all made of nonmetals. And if you've forgotten, the nonmetals are where on the periodic table? On the right-hand side. They also sometimes have metalloids. So you can see those are the blue ones here. Okay, so that's our silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, and whatever else. Okay? They can be really, really simple. I2. Is that an element or is that a compound? That's an element. I2. Then we can have HBr. Is that an element or is it a compound? That is a compound because it's got two different elements. HBr. And you can see there's all kinds of other ones. We have P4, we have H2O, we have IF5. Sulfur does a funky little thing where it forms this like ring of 8 sulfurs that looks a little bit like a crown, okay? And then we can even get something like, I think that perhaps this is caffeine, but I'm not sure. But if we zoom in, you can see it's got carbons, okay? It's got nitrogens. And if you wanted to spend your time counting them up, you could write a formula for this thing. Yes? It's got oxygens. Come on. So if we had to write a formula for this, we actually could count them. How many carbons do we have? We have 8, so we would write C what? 8. Where's the 8 go? Top or bottom? Bottom. And then usually we write the hydrogen next. H, and there's a lot of them. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Are there 10? Yeah. And then if we were to write nitrogen, how many nitrogens? 4. And then O2. And then we're done, yeah? Did I miss some? I think it might be caffeine, but I might be wrong. Okay, there's a lot of very complicated organic compounds. Organic compounds are the ones that are based upon carbon. So which is why when people say they're eating organic food, it does make me laugh a little bit because all food is organic because all food is carbon based. But that's not what it means in a technical sense in the grocery store. Okay, so anyway, you can see there are tons and tons of different molecules. Some of them are big, some of them are small, but always it's nonmetals. Molecules can be elements, and that means the atoms all have to be the same. So if you look at all of these, we've got all the diatomic elements. What does diatomic mean? 2 atoms. So our diatomic elements, di means 2. Di is the prefix we use in chemistry. I don't know why they chose that rather than bi. I think bi means you split it in 2, but I could be wrong. I don't know. It's very strange. Okay. And we have the diatomic elements. And you are going to be expected to know these for this test, so I'm going to give you several ways of remembering. Okay? And I've got them written down a little later on, but we're going to talk about them now because one of the ways is really easy to see right here. Okay, so we're going to go close. You can see on here the purple ones are the diatomic ones, so it would be H. When hydrogen is on its own, it's always H2. When nitrogen is not paired with another element, it's always N2. So, one of my students this year taught me a new way of doing this. They call it the hockey stick and the puck. Can you see the hockey stick and the puck? Okay. How many diatomic elements are there? Can you count them for us? How many? There are 7 diatomic elements. Can you guess what atomic number nitrogen is? Or do you know what atomic number nitrogen is? It's number 7. And what number does this hockey stick look like? It looks like a 7. So you go to element 7, you draw a 7, and that's your hockey stick, and then your puck is hydrogen, so that gives you 7 elements altogether. Okay? There's another way. This is the way I learned it in high school because nobody taught me any of the neat little tricks to remember it. I used to say H-O-N, halogen, because it just sounded like really easy to remember. And you got like pom-poms or whatever. H-O-N, halogen. Can you tell I was not a cheerleader in high school? Okay. So we have hydrogen, nitrogen, oxygen, and then we have the group 17, which is the halogens. The one that everybody got taught in first year university is Dr. Brinkelhoff. Okay, so you got bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So you can remember that. But a lot of people have their favorite one because it's inappropriate. It's not terribly inappropriate, but inappropriate things always make it easier to remember. Have no fear of ice cold beer. Yes, it rhymes. For grade 9s, it's minorly inappropriate for me to be telling you that, okay? Although I do feel like I did my PSA for, not drinking until you're older last week, so maybe I can get away with that, okay? This doesn't mean you should have no fear of ice cold beer. Remember, alcohol is a carcinogenic, causes cancer, it causes liver disease, it causes damage to your brain, especially when drunk in a binge drinking fashion. So don't binge drink whatever you do. That one's the really bad one, okay? That just hurts your cells like nobody's business. Anyway, those are your ways to remember it. You pick the one you like or the ones you like. Okay, you are not expected to know that phosphorus is P4 and sulfur is S8. I've just put them in there because it's interesting to kind of look at those molecules, okay? There are other polyatomic molecules, elements. Molecules can be compounds, which means they contain different types of atoms. So we have water, which is made of oxygen and hydrogen. What kind of a bond is that right there that the arrow is pointing to? What kind of bond? That is a covalent bond. And a covalent bond is strong. Okay? Covalent bonds are strong. We have ammonia, NH3. Carbon dioxide, CO2. No, that's not carbon dioxide. What am I doing? Carbon dioxide is down here. CO2. This one is water, H2O. And methane, what's the formula for methane? Tell your partner, what's the formula for methane? This one here. C and then H4. You don't have to worry about what order they go in yet. If you said H4C, that's fine. No worries, okay? If you are doing the enriched stuff, you should memorize the name and formula of ammonia and, whoa, not crossing it out, ammonia and methane. However, if you're not doing the enriched stuff, don't worry about it. It's not that important. Not in grade 9 for sure. Molecules are always 2 or more atoms. So if we have this guy right here, this is not a molecule, right? Because it's only got 1 atom. So that is a molecule of oxygen. This kind of oxygen, O2, this is the oxygen we breathe. O2. Okay, this is a molecule. And then there's another kind of oxygen which has 3 O's, and that is called ozone. Does anyone know where you would find ozone? Yeah, it's way up in the atmosphere in what they call the ozone layer. Have you guys heard of that? It's super important because it actually it absorbs the UV rays from the sun, so only a small amount actually gets through. If it wasn't there, we would fry. Yeah? So back in like the 90s, it was a huge problem because there were these chemicals, chlorofluorocarbons, that were like chomping their way. They would cause a chemical reaction in the ozone layer. And have you heard about the hole in the ozone layer? It's actually doing much better than it was then, but at that time it was getting bigger and bigger and bigger, and it was very, very worrisome, and it was right above the South Pole. So it's better now because they've banned those chemicals that cause the breakdown of that layer. so we won't fry, which is a good thing. So this is a molecule. Atoms bond covalently, which means that the pairs of electrons are shared. So you can see we have our shared electrons here and here. Do you remember what we call one pair of shared electrons? That's called a single bond, and we would show it like if I had element X bonded to element X, what would I show to show a single bond? One line. Double bond, 2 lines. Triple bond, 3 lines. It's pretty straightforward, right? Okay. Ooh, what model of the atom do we have here? That's our electron cloud model. Yes? Yeah. Okay, and you can see we have one pair of shared electrons gives us our single bond. 2 pairs of electrons gives us our double bond. And just to mention it here, this kind of model is called a ball and stick model. Because guess what? It's made up of balls on the ends of sticks. Yes? Ball and stick model is very descriptive. And you can see, oh my gosh, nitrogen is really fancy. How many pairs of electrons does nitrogen share? How many pairs of electrons? 3. And that's our triple bond. Okie dokie. I'm not going to go on much about molecules having definite composition. We did talk about it before. It is an enriched topic, so if you want to read a little bit more about it, you can. Point number 7. Ionic compounds do not form molecules. What is different? What do you see in the ionic compound that prevents it from being a molecule? We see a metal. And if you have a metal, it is not a molecule. What else do you see? We see charges. Therefore, it's not a molecule. Okay? Ionic compounds bond ionically. That electron gets transferred, of course. That gives you the positive ion that attracts to the negative ion. This is an ionic bond, not a covalent bond. Our electrons here, they instead of being given one to the other, they are shared, okay? And this is a neutral atom bonded to another neutral atom. Whereas in the other one, we have an ion bonded to an ion. This is just kind of showing, we've done a whole bunch of this, I think, already, so I'm not going to go into too much detail on that. This is enriched. Molecules contain an exact number of each type of atom. Although ionic compounds have a fixed ratio, maybe we have Na90 to Cl90, and that's ionic. We could have a bigger crystal, which is Na 1000 to Cl 1000. And so that is not a molecule because it can have different sizes. Yes? Okay, that is though an enriched point. So if you're not interested, don't worry about it. Okay. Now, do you remember what we call the forces between molecules? Intermolecular forces, because inter means between, so obviously between molecules is intermolecular forces. How do we abbreviate intermolecular forces? IMFs. This again is enriched material, but that's okay. They are significantly weaker. These are very weak. Covalent bonds are strong. Ionic bonds are strong. IMFs are weak. Covalent bonds, ionic bonds, and even metallic bonds are all strong. Whereas the IMFs are very weak. So that's why when you boil water, it's going to be those weak forces that break rather than your strong covalent bonds. Do you guys know what metallic bonds form between? Metals and metals. And you don't need to know anything about them other than that this year. They're strong and they form between metals and metals. Okay? So here we go. We have the strong covalent bond right in the molecule. Here's another strong covalent bond in the molecule. And in between them, we have the weak intermolecular force. So if we heat that up, what's going to break? The weak intermolecular force will break. Okay? In the NH3, we have a covalent bond. Did I go up too soon? You want me to go back? No, we're good? Okay, sorry. Okay, so we have the covalent bonds, and then in between the molecules, we have our intermolecular forces. Okie dokie. And this is just sort of carrying on with the same idea, and this just shows you who is going to break. So if we have liquid water and we heat it, you still have water. The covalent bonds have not broken. Yes? It is those weak intermolecular forces that break. So what you're not going to see is you're not going to see, oh, I'm going to boil some water, and all of a sudden, I have hydrogen and oxygen atoms all together, like just separated out. Okay, that does not happen. You cannot get that to happen. Do you remember what sublimation is? Sublimation. That is solid to gas, yes indeed. And so if you have something like carbon dioxide is one of the really weird things that actually does sublime. We've got carbon dioxide solid over here. And you can see there's those weak intermolecular forces here. Within the molecule, we have those strong covalent bonds, and those stay intact, but the weak intermolecular forces have broken when we heat it. And this would be, oh, I've written it there, CO2 gas. Oakley dokley? That's why if you ever see CO2, it like sort of gives off this mist. It's quite exciting. Okay. Here are all the different ways that you can represent molecules. You don't need to know the names of all of them. I think it's handy to know maybe the space-filling model and the ball and stick model. Just because those are the two you'll most often run across, but we've got our structural formula, right, which is pretty straightforward. We have our electron shell diagrams that we're going to focus on drawing in the second part of class today. And then, of course, there's the molecular formula, which is just the simplest way of writing it that you can possibly imagine. Okay? And once again, down here, we have your little mnemonic devices. Do you guys know the word mnemonic? Mnemonic is to do with memory. It's got a silent M at the beginning, because of course we all need a silent M. Who can't do with a silent M in their life? And it's pronounced mnemonic. That doesn't look like an N. A mnemonic device helps you remember something. So you'll hear that from time to time. So we have our mnemonic devices. We have Dr. Brinkelhoff. We have our hockey stick and puck. Start on element 7, draw a 7, and add that 1 for the puck. That is hydrogen. Have no fear of ice cold beer. And the one that I used to use, but it does not seem to be a crowd favorite. That's okay. I'm not offended. HON. Halogen. Woo. Okay. Page 66. Alrighty, page 66. At the top of the page, there is just a reminder of how you remember your 7 diatomic elements, okay? Because apparently I thought it was important enough to put many different places. But at the bottom of the page, Kennedy, could you get the door for us, please? Thank you so much. Oh, much better. So covalent compounds, we had looked at the bonding in elements However, if you want to show covalent bonding in compounds, and remember, these are dot and cross diagrams. So when you are drawing them, the electrons in one element should be dots, and in the other element it should be crosses. Hence the term dot and cross diagram. Yes? It doesn't really. Okay? Either way is fine. So if you choose, put the X's here and the O's there, doesn't matter. Okay? So you can see here we've got hydrogen and chlorine. And chlorine, we've used the dots. It's got an empty slot right there. Yes? And hydrogen, which needs only 2, has an empty slot there. We can make sure that chlorine has a full 8 electrons by sharing, and you show the shared electrons. Remember, those go in the area in between. And you know that one of those shared electrons came from hydrogen because it's drawn as an X. And you know that one came from chlorine because it's drawn with an O. Okay? If you are interested in this kind of thing, acids are compounds that begin with hydrogen. That's, again, a black diamond sort of thing, and you could memorize the formula of hydrochloric acid, which is HCl. Okay? But those are enriched stuff. Let's take a look at CO2. Here we have carbon. How many holes in carbon? How many holes in carbon? 4. 1, 2, 3, 4. So how many bonds will carbon tend to form? Carbon will tend to form 4 bonds. Oxygen. How many holes in oxygen? 2. 1, 2, and 1, 2. So in order for everybody to have the right number of electrons, oxygen is going to have, each oxygen is going to have to share 2 electrons to fill in the holes in the carbon, yes? So what we'll end up with then is 2 electrons from oxygen A, the X's, and then 2 from the carbon, 2 electrons from oxygen B, and 2 from the carbon. And then we have lone pairs of electrons. And lone pairs of electrons are non-bonding. Okay, so we got a lone pair there and a lone pair there, and we have the same thing on our other oxygen. Yeah? How many pairs of electrons are being shared between carbon and oxygen? 4. So what kind of on just between 1 carbon and 1 oxygen? 2 pairs are being shared, like say right in here, yes? And then there's 2 pairs shared on the other side. What is this bond then if it's 2 pairs being shared? That's a double bond. Okay, and you can see that in our structural formula where we have O and 2 lines and then a C and then 2 lines and then an O. Yes? Here's H2O. This one's a little more straightforward. We have 2 holes in oxygen and 2 holes in hydrogen. It is totally optional for you to draw in the holes or not. If you find it helps you, you can do it. If you don't find it helps you, then don't bother, okay? So, we need to share these guys. And we need to share these guys. Yes, so we have our shared pair over here, we have our shared pair over here, and we have H2O with a lone pair on the oxygen on the top and a lone pair on the bottom, which should always, how many should we have if we count all the way around oxygen? We should have 8. 1, 2, 3, 4, 5, 6, 7, 8. That gives us a complete what? A complete octet, yes. Okay. And if we look at our carbon up here, if we go all the way around this carbon, we have 1, 2, 3, 4, 5, 6, 7, 8. Carbon's good. If we look around our oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8, and the same with the oxygen on the other side. Everybody has 8, so that's good. The only one that doesn't need 8 is, who doesn't need 8? Hydrogen, because it only needs 2. Everyone else needs 8. Okay, we're going to skip the exercises for now, and we're going to go to 3.4b. Okay, I'm going to leave the word bank questions for you, and I'm just going to explain how these exercises work. Okay? So we are on page 68. There are 4 levels of tasks. They get more and more difficult from level 1 to level 2 to level 3 to level 4. You are expected to try at least one task from each level. If you find level 1 really easy, do you have to do all the level 1 tasks? No, you can move on to level 2. If you find level 2 really easy, you can move on to level 3, and so on. If you're finding it at all difficult or like challenging, then you can do more of the tasks. Yes? Make sure that you're using both dots and crosses. One of the things that people forget to do is to put crosses on one of them because we've been drawing dots for so long for electrons. Yes, so that's a change in how we're doing things here. Don't forget to draw arrows to show the movement of the valence electrons from the metal to the non-metal. You're going to make sure you write the charge of the ions. You're going to do at least 3 tasks that show the full electron configuration. Once you've done that, you can leave the core electrons, the inner electron shells blank, and just show the valence electrons. Does that make sense? Because doing 3 will remind you how Bohr models work, but it gets tiring to draw all those dots and crosses. So if you just want to show the valence shell after you've done 3 with the whole thing, then you can do that. Is that good? Okay. You are going to give the name of the compound. Don't forget to change the ending to "-ide" for your non-metal. It goes metal, non-metal, and then change the ending to "-ide." And you're going to give the formula of the compound, and you're going to use subscripts to tell how many. We're going to do one of them together, and then you can try the rest. Once you are done the ionic ones, the covalent ones follow right after that. You can just carry on right into the covalent ones. It's fairly self-explanatory. If you get stuck, call me over. I'm going to be coming around and checking homework while you're doing that. But yeah, so here's an example. We have a potassium. And remember, potassium is atomic number 19. Okay? So how many electrons does potassium have? 19 electrons. And if you fill them in, you'll end up with 1 electron on the outermost shell. Sulfur is atomic number 16. So how many electrons does it have? It has 16 electrons. So you'll fill in 16 X's, okay? Then you're going to say, oh, where do I have holes? If it helps you to draw the holes, you can do that. If it doesn't help, you don't have to, okay? You have to, though, show the arrow, saying this electron is now moving over there, and this electron is now moving over there. Yes? So this is what we have before the bonding, and this is what we have after. Okay, so we have a before and after situation. So before, we have the neutral atoms, and after we have the ions. So you can see we have the potassium, okay, and it's missing that outer shell now because that outer shell is now empty. It lost one electron, so we have to write that it became positive. Same thing with the other potassium. And because we had 2 extra electrons now in the sulfur, it is 2 negative. When you go to name these, don't forget that it goes metal first and the nonmetal second. So we would name it potassium, and then the ending of the second one changes to "ide." Just a little hint, you don't ever want to have 2 vowels in a row. So which of these would be correct? Which of those is correct? Oxide, okay. How about, let's see, what's another one? Nitride, not nitroide, okay? So you're always going to kind of want to get rid of that vowel. If there's a vowel there, you don't want it hanging out before your "ide", okay? Because we have 2 potassiums, you can see we got 1, 2 potassiums, it's going to be K2. We have that little subscript, sub meaning below, script meaning writing. Below the writing, we have a 2 telling us we have 2 potassiums. What do we do if there's only 1 of an atom? Do we write a subscript? No, we just write nothing, okay? So do you feel like you have enough tools to try that on your own? And don't forget, if you decide once you've done 3 of them with the full configuration, if you just want to use valence electrons and just show the outer shell, how do you know how many electrons are in the outer shell? Like if I were to go here, how would I know how many electrons are in the outer shell of group 1? How many valence electrons in group 1? 1 valence electron. How many valence electrons in group 2? 2 valence electrons. Do we know anything about the transition metals in the middle? No, we don't. How many in group 13? 3 valence electrons, 4 valence electrons, 5, 6, 7, and then technically it's 0 because there are electrons that are involved in the bonding process, so we don't have any there. Okay, if you said 8 though, I wouldn't get mad at you because it's not quite, yeah. Anyway, so do you feel you can go ahead with that? And you'll call me over if I have not come to see you yet and you're having difficulty?